differentiate y equals 3 times tangent of e to the x power. All right, so we got a trig function here, but we also have this guy in here, right? So this is a composite function. Now the 3, it's a coefficient, right? The constant term doesn't really change the problem at all. Of course, we do need to keep track of it. All right, but how do we deal with this? Right, so once again, this is called a composite function. Now, for example, if we have just tangent of x, right, y equals tangent of x, then what is the derivative of tangent of x? Right, well, the derivative of tangent of x is secant squared of x. Okay, but does that mean that the derivative of this is the derivative of this is secant squared e to the x power? And the answer is no, okay, because of this composite function here, right? Okay, so how do we deal with that? Well, the outer function, we'll just call that tangent of x. Right, and in this case, the inner function is e to the x power. So as we can see, if we compose these, right, we do get that tangent, and instead of putting x here, right, I'm going to substitute that guy in, so we get e to the x power. Okay. Of course, once again, the 3 doesn't make that big of a difference here, right? We just remember to stick a 3 in the final answer. So then how do we take the derivative of this guy using the chain rule? Right, so first we take the derivative of the outer function f of x, right? So the derivative of tangent, so once again dy dx here, what's it going to be? Well, I know what the derivative of tangent is, right? It's secant squared. So 3, derivative of tangent is secant squared of e to the x, right? That doesn't change. Okay. But then what's the next step here? Right? By the chain rule, we have to take the derivative of the inner function. And in this case, the derivative of e to the x is just e to the x. Okay, so if we just rearrange the terms here, we get 3 e to the x secant squared of e to the x. And this would be the derivative.